about OpenMind, and I was like, this is cool, but I didn't really have the time to like get deep into it, and I'm really pleased Adam has, so I'm looking forward to it. Thanks a lot.
Awesome, yeah, thank you. Where's the slide? Oh, is this it? Maybe? Perfect, okay, cool. All right, wow, thank you for everyone for coming. Today I'm going to be talking about privacy-preserving AI techniques. So I wouldn't say that these are sort of totally solved techniques. I would say that the main topic that we're going to be looking at today is what are sort of the needs for privacy and sort of machine learning and data processing, data storage systems. And we're looking at the convergence of sort of 3 different areas that actually are relatively mature. So we'll be looking at federated learning from machine learning, secure multi-party computation from cryptography, and then differential privacy from kind of cryptography and database statistics. And even though these are sort of being developed in different communities, what we're advocating for in OpenMind is that they actually should be working together in sort of one cohesive unit because they sort of solve each other's problems. And so the main topic I'll be going through today is sort of a high-level introduction to the theory and why these things work. There won't be too many formulas, but a sort of intuitive understanding of how these approaches work and why they're relevant. And then, yeah, just a bit on sort of what we're doing in OpenMind to try to embed it into PyTorch and TensorFlow, if you're familiar with those deep learning techniques. Cool. So first, a quick outline. So we're walking through kind of the general goal of privacy and like our motivations, and then we're going to narrow down to what specific canonical problem we seek to solve that is sort of general enough for the rest of the things to generalize from it. Then we're going to look at our strategy for adoption and more the timeline of how these things are happening. So first, if we think about asking the question sort of what is privacy, right? And most people, when they think about privacy, they think of you know, a locked door or curtains closed in or your keys sort of kept perfectly hidden. And maybe more generically, they think of no information leakage. They think of sort of, you know, a safe that is perfectly private, right? That would be kind of people's definition of perfect privacy. But what I would sort of advocate here is that privacy is actually not about mitigating all information leakage, because there tends to be a pretty negative trade-off when you do that sort of in all areas of your life, right? And so the definition of privacy that we'd like to propose is that actually you have primary goals like fairness, equality, justice, safety, these kinds of things. And there's actually a balance between privacy and transparency that you want your technology to be able to facilitate, which optimizes for these sort of primary goals. So if you think about if perfect privacy is hiding all information, then you know the activities that you do at your employer, for example, right? If we never knew what anyone did at their employers, for example, and you know those individuals have perfect privacy, it would be very much harder for us to be able to keep those sort of large institutions accountable. Does that make sense? How there's a balance between information we want to hide and information that we want to reveal, which maximizes our primary goals, right? Cool. So we can see this a little bit better in when looking at privacy kind of in context. So for sort of researchers and product developers and these kinds of things, you have this sort of interesting balance where the more information you have access to, say the more maybe radiology scans you have to work with, the more accurate classifiers you can construct, and the sort of more progress you can make on certain diseases. So like there's a great guy named John Gallagher at the University of Oxford who's trying to understand dementia. But he has access to so little information, so little data, that one of his main pushes at the moment is to actually further these technologies so that he can have access to more information about dementia while also having better privacy protections for the individuals that he's working with. And these, again, this sort of privacy and transparency trade-off might seem like something, you know, it's sort of like a zero-sum game, but what we'll actually find is that we can make meaningful progress on having sort of both at the same time. So a few of these I'll touch on a little bit later. But just to highlight kind of where this trade-off tends to show up in society. So if you look at privacy versus innovation is kind of the one I just sort of referred to, right? So we have lots of researchers wanting to cure cancer and understand the human body and all these kinds of things, but in order to do that, they have to study human bodies, which means they need access to data that is potentially sensitive, that could potentially harm individuals, right? So the more information that we can release, the faster we make progress on certain diseases, and the less we release, the safer individuals are, or so it would seem, right? But what we're going to look at in these tools is that we can design very interesting filters that allow us to have sort of a better trade-off than we had before. I'm not saying that it's absolutely perfect, but I think that if right now we have to answer questions like, do we give them the data or do we not give them the data? Instead, we can say, like, as in, do we give them the medical record or do we not give them the medical record, right? Instead, we'll be able to ask questions like, do we let them know this piece of information is contained in the medical record or not let them know this piece of information is contained in the medical record? Can we tease out exactly what they're looking for and restrict what they're not looking for? Can we have an image of a patient that has a tumor in it and allow this researcher to learn what tumors look like in humans without necessarily learning whether this person actually has a tumor in this particular image, right? So, and we'll come at this from several different angles, and I hope this makes sense in a second. But just to highlight a couple, so privacy and security, same idea. You're going to the airport, there's a kind of a perceived trade-off there. Privacy and accountability is something I referred to a minute ago. So you have lots of private individuals, working together in sort of some large organization. You want to be able to hold the organization accountable for its actions, right? But you also want to protect sort of the privacy, security, maybe the intellectual property of the organization itself. Like, how can we do both? It would seem that this would be sort of impossible in the analog world. Cool. So let's talk a little about. I'm going to skip that for a second and come straight to here. So let's say you go to the doctor. Okay, a doctor and a patient are basically going to try to compute a function together. And this is the canonical setup, right? So this is the sort of human performing a service for another human model in the analog world. And it involves private data. And actually what we'll find is, if we can solve it in this case, it generalizes to a vast number of cases in the real world. And actually all the ones that I was referring to in the previous slide, okay? So let's say I'm a doctor and you're a patient, okay? And so we're each bringing sort of our own private data set that we want to be able to keep sort of secret, right? But there's certain things that we want to have happen in this interaction, okay? And the result of this interaction is we're going to compute a function on our two private data sets, which is what treatment either patient should have, right? So it's some function of private data. So the patient's private data set is their medical history, obviously. It's their current symptoms. It's even who they are, their family history, like where they live, what kind of environment they're in. Like all this is sort of a data set that the patient is bringing to this interaction. The doctor is bringing a different kind of private data set. The data set that they're bringing is sort of medical expertise, right? So it's a little more of the sort of proprietary IP sort of flavor, right? But then it's also the doctor's previous history working with lots of other patients and things that the doctor has sort of learned over their career, right? Which does involve actually quite a bit of private information. And so what the doctor and the patient want to be able to do is combine their information in this sort of medical procedure function to produce this treatment, okay? So now, what are our desires, right? Well, there's a few. And the first one is each one kind of wants to keep their own information private, right? The doctor shouldn't start spouting off about other patients that they're working with and their private conditions as a function of giving you treatment. On the flip side, the patient ideally would like to not have to disclose all their most personal and private details in the midst of the procedure, right? So in an ideal world, they wouldn't have to disclose their private information to anyone. And most likely when they're sitting in the inspection room, they're going to make some sort of judgment call on what information is relevant and try to release sort of the minimum information possible. Does this make sense? But secondarily, we have something that is actually kind of a difficult challenge to do at the same time. Each person wants to verify that the other person is bringing legitimate information. The patient wants to know that the doctor is actually qualified. The patient wants to know that the doctor, when they worked with other patients, those patients actually got better, right? So on the flip side, the doctor wants to know that the patient is actually revealing all the symptoms that are relevant, right? That they're maybe not hiding the ones that are actually quite important to making sure they get healthy for reasons such as embarrassment, or they forgot, or they don't think it's relevant, all these kinds of things. So we have mutual secrecy. Everyone wants to keep their information secret, ideally, but also a mutual desire to verify that the other guy's secret information is the real deal, okay? Then we have the question of how we actually verify that the computation that we're doing together is correct. Are we following correct medical procedure? And finally, we have output privacy. Output privacy is about whether or not we can reverse engineer inputs from the patient and doctor as a function of the treatment, right? Can I say, oh, you prescribed, polyethylene. Oh, I made that up, I don't know. And so now I know that you have, bleeding in an uncomfortable area or something like that. Like, can I look at the output and then infer something about the input, okay? So these are slightly different. So input privacy is about whether the patient can learn lots of stuff about the doctor and vice versa as a result of them computing together. And then output privacy is about whether I can reverse engineer the output back from the inputs, or the inputs from the outputs. Does that make sense? Okay, cool. So this is what we're going to try to solve. And the interesting thing is that I'm going to advocate that we can actually do a better job at both protecting the privacy of individuals and verifying that people are bringing the appropriate inputs in the digital world than we can in the analog world. In the analog world, you have to tell the doctor all the information that's relevant. You have to tell another human being and then trust that they will either not communicate it or forget it, right? That is, and most of the time, a doctor, okay, obviously if you're working with the same doctor over a long period of time, maybe they become someone who's not a stranger, but by and large, it's someone that you're sort of randomly affiliated with, randomly assigned, right? But in the analog world, we'll find that for the very first time, maybe ever, we can interact with something that has some level of intelligence that can prove that it forgets something when you leave, okay? And this is why machine learning, or artificial intelligence, I guess, if you want to use that word, is so useful for privacy in this context. Because we can compute over information and make formal guarantees that what's left over is not storing anything, right? Using a combination of machine learning and cryptography, which is what this talk is going to be about. So in this particular case, one great canonical example is that you can have a cancer predictor, piece of machine learning. It's predicting whether or not there's cancer in an image, for example. You have an MRI image, piece of data coming from the patient, and then you compute an output function, which is the probability that there's a tumor in this image, for example. Okay? Let's see. What I pointed. We might be on this slide for a while. Oh. Okay, cool. So what's the strategy? There are 5 things that make this hard, okay? First, data is trivially copyable. If I give you a file, it is really, really, really hard, nigh impossible, for me to prove that you delete that file or that you send that file somewhere else, right? So that's sort of, the first challenge we have to overcome, or else all the things I previously said are impossible. Secondarily, data is trivially modifiable. If I take an image, give it to you as a doctor, and you futz with the image and change it and do all this kind of stuff, and then compute the output of the function, right? Maybe you drew a little tumor on there and then made the prediction so you can sell more pills, right? It's hard for me to know that you did that, right? Thirdly, data, when it's generated, is highly distributed, right? So let's just say, for the sake of argument, that I wanted to do some study, right? But I wanted to make sure that all of you held on to your data and didn't have to give it to me. That means I need a piece of infrastructure that lets me work with data that's on, 150 phones. How many people are here, right? Or 150 other devices that you control, right? This is just an interesting piece of infrastructure that is different than centralizing all data. Fourth, I know it's about cryptography, I can't count. So complexly embedded. This one's a bit challenging. Okay, so I have an image of a patient's torso, X-ray or MRI, something like that. How much of that image is private information and how much of the image is public information? Anybody want to throw something out? You can say all, either way.
It depends.
On what?
Whether it's personally identifiable.
Ooh, exactly. So it depends on whether it's personally identifiable or not. Another way that I like to say this is that consider the fact that this is a mixture of both, right? So if I have a picture of a human torso, right, I might be able to tell, okay, this human has 2 arms and 2 legs, right? That bit of information is not particularly unique. It's not personally identifiable, right? I might be able to tell that this person has a lung on the left side and a lung on the right side. That's not new information, right? But mixed up with this information is also the particular shape of this person's heart, right? That might be sort of uniquely identifiable if you had some other way of matching hearts to people, right? So there's a mixture of both unique information with stuff that all humans have, right? And the really interesting bit, and this is why we can make a lot of progress on this, is that science is chiefly concerned with the things that lots of humans have in common, right? If I did a bunch of statistics and then figured out that if you had a heart that looked exactly like this, here's your probability of cancer, It's not very useful because no one else is going to have a heart that looks exactly like this. I want to be able to say, all right, here's what tumors look like in general, right? Here's how human bodies tend to decay, right? That's the statistics that I, as a scientist, are after. That's when we're building a product or a service that billions of people can use. We care about the patterns that are happening over and over and over again in billions of people. And that, by definition, means we're after the stuff that's not private, even though we have to interact with private information to get it. Does that make sense? So the goal of these techniques is to build tools to make it so that we can reliably extract just that information and reliably leave behind the private bits, the bits that are person-specific, personally identifiable, right? How am I doing on time? I can't, there's no, good? Okay. Loosely speaking, as I mentioned, there's a host of fields working on different aspects of this problem, and I'd like to give you a quick survey of them, okay? And here, so we look at encrypted computation, verified computation, federated computation, data filters, and signatures. Signature technology, I think, was what was touched on in the last talk. Specifically, I'm going to focus on a subset of these. And I also want to mention, so in the OpenMind project, so it's kind of OpenMind but spelled like data mining, we're working on embedding these technologies into the major deep learning frameworks, so you don't necessarily have to understand the cryptography side or the deep statistics side to be able to use them, to sort of lower the barrier to entry for people to be able to play around. So if you're interested in this, interested in collaborating with Adam and myself, please do check out the OpenMind project. So there's a few different algorithms we're going to look at. We're going to focus on secure MPC, federated learning, and differential privacy. We did a bit of an export from my keynote file, so do forgive the disheveled nature. Cool. First, we're going to start with differential privacy. So, differential privacy is about making formal guarantees on how much private information you're leaking when you publish a bit of data. Okay? So it started with database queries in around 2003, or sorry, yeah, 2003. And the premise here was I've got a big database full of private information, and I'm going to have a query against that database, publish the result, and I want to answer the question, is any private data being leaked, right? And there was a lot of progress made on this problem, and it's been generalized for use inside of machine learning. Cool? So first, we got to look at a robust definition of privacy. If you were to Google privacy, as I did, this is the kind of definition you find, right? After an analysis, you don't learn anything about people in a data set, they remain unobserved. Not learning anything about people comes at a huge trade-off with regards to, what? Accountability, innovation, security, all these sort of things about when you hide information perfectly, right? As we mentioned before, there's lots of positive benefits we can receive as a community if we can instead say, okay, I'm not going to release anything personally identifiable, but I am going to look for patterns of what it's like for humans, right? Things that are not personally identifiable and try to release that. So this definition, basically, it's a little bit too simple, right? And it doesn't really reflect the kinds of activities that we want to be happening inside of commerce. It's overly zealous to the point that it's actually damaging, again, on the other side. This one gets quite a bit closer. Anything that can be learned about a participant from a statistical database can also be learned without access to the database, right? So the idea is, if someone has published some private data online, and then I do a statistical study here, and I learn private information about them, but it happens to be the stuff they already published, then we're good, right? This one's really hard, first off, because it doesn't actually get at the notion that private information, even if you're propagating it yourself, can continue to be damaging. So this is sort of the opposite. This is too relaxed, right? Because even if someone has released private information in some part of the online sphere, you continuing to propagate that can continue to cause more damage in that person's life, right? So we need something that's a bit of both. So Cynthia Dwork, who won this sort of a really big prize in computing for coming up with both the formal definition of differential privacy as well as this sort of nice semantic definition, said this. So she said, privacy is preserved if you will not be affected adversely or otherwise by allowing your data to be used in any study or analysis, no matter what other studies, data sets, or information sources are available. Okay? This is really, really important, especially that last little bit, no matter what other information sources are available. As it turns out, the really, really hard part about protecting people's privacy, specifically output privacy, so when you're going to be publishing something, is not just the information that you publish. It's what other things can be used to link against that. Case in point, Netflix Prize. Anybody familiar with the Netflix Prize? A big machine learning competition. Okay, so a few years ago, maybe 5, 6 years ago, Netflix took their big movie ratings data set, all the people that have rated their movies, right? And they replaced all the movie names with numbers, so 0 through, I don't know, 40,000 or something. And they replaced all the usernames with numbers again, so 0 through 100,000. So just a big matrix of movie ratings. And they said, all right, all you machine learning people, whoever can predict the missing values that we pulled out of this, so they removed some of the values and deleted them, whoever can predict the ones that we remove with the highest degree of accuracy, we'll give you $1 million, right? And the interesting bit is that you might think, this is a totally anonymized data set. There's no PII at all, right? But what people were able to do within some researchers in Texas, within about 2 months of this data set being published, is they went over to IMDb and they scraped IMDb and found a bunch of other people that rated movies. As it turned out, there was a pretty big percentage of people who were passionate about rating movies and rated a bunch of movies on IMDb and a bunch of movies on Netflix, and they're able to join them back together and de-anonymize a large percentage of the data set. And actually, it turns out, once you start de-anonymizing parts of it, then you get enough context to start de-anonymizing a lot of it. This has been done with anonymized medical records. There was like a senator's medical records were published. This is done with anonymized search queries for some search data sets that were published. Data set anonymization, by and large, just removing the PII, is not sufficient. So if you don't remember anything else from this talk, remember data anonymization does not work. You need to have a robust technique like differential privacy that can actually measure the amount of unique statistical signal, right? It doesn't matter whether or not their social security number, well, it does matter if the social security number is in there, but like deleting the social security number is not enough, right? If there's a certain level of uniqueness that you're publishing, right, that is enough to link back to the person, right? So what we need is a measure of like, if I'm going to publish a result of computing, like, so if I'm going to publish some result of computing on everyone's data who's here, right, the question I need to answer before I can do that is, are the patterns that I'm releasing in this publication, right, in this statistical model, this AI model, this survey, this histogram, right, whatever I'm publishing, right, can I prove that the patterns that I'm releasing, at least, 5, 6, 7 people all had them when I'm releasing them? Like if I say, smoking causes cancer, right? If there's only one person in this room who smoked and then got cancer, that's PII at this point, right? In respect to this data set, it's PII. It's unique to one individual, right? So any findings that I publish should have multiple individuals who are contributing to that conclusion, right? Otherwise, it's possible that it could be traceable back to one person if I've got another substitute data set. Does that make sense? Does that intuitively make sense? Okay. I need to pick up the speed a little bit. 5 minutes? Okay, cool. Cool. So I'm going to go through one example here, and then we're going to race on to the next thing. So in differential privacy, if you read the literature, you have a canonical database of 1s and 0s. 1 corresponds to true, 0 corresponds to false. We don't really worry about what they're actually talking about because we're just working on, we just assume this is a sensitive attribute or a private attribute. We compute a function and we say perfect privacy would be such that the output of our query is the same between this database and any identical database with one person missing, okay? Meaning, put another way, if I removed any person from this database and the output of my query did not change, that query has, perfect privacy, okay? Why? Because it means the query is not actually dependent on any one specific person. Does that make sense? So if I remove any person from the database and my query does not change, right, then no specific person's specific information is being leaked through that query. Okay? Now, as it turns out, most useful queries, like sums and means and standard deviation, all this kind of stuff, doesn't fit that property. But that's the unit of measurement that we use. Cool? And so the amount that the output of the query would change if we remove something from the database is called sensitivity. Right? That's a key input to calculating privacy. So we could look through sum. So sum, in this case, it's a database of 1s and 0s. So the sensitivity of this query would be 1, because the maximum that the function could change if I remove person is 1. Does that make sense? Got such good stuff. Okay. Yeah, I'm going to do this one, and then we'll go really quickly through the next one. Okay. So my sister, I have a twin sister, she does political science. And in political science, they have this exercise where they add noise to give people plausible deniabilities that they are willing to disclose private information. And here's how it works. Let's say I'm going to ask you a true-false question, okay? But about a taboo thing. So like whether you have ever murdered someone or, I don't know. Yeah, we'll go with that. That's fine. So I distribute coins to all of you. You all flip the coin in a place that I cannot see, I, the surveyor, cannot see, okay? And if the coin is heads, you answer me honestly, whether or not you have committed murder. But if the coin flip is tails, you answer according to your second coin flip. 50-50 chance, yes or no, okay? And the really cool thing about this is that I, upon receiving your answer, have, I don't know if you're answering honestly or if you are answering according to a 50-50 coin flip. So if you say, yes, I am a murderer, then you might be a murderer, but you might just have had the correct series of coin flips such that you give me that answer. However, in aggregate, when I look at all of your answers, right, I know that I'm taking whatever the true answer is and averaging it with a 50-50 coin flip, right? So if 55% of people say yes, then in expectation, 60% of people were murderers. Does that make sense? So we can use noise to give people plausible deniability on their inputs. And this is what the field of differential privacy really does. It allows you to calibrate the amount of noise that you need to add to the results that you're publishing so that people have a certain degree of protection, right? And the amount of noise that you add is dependent on the sensitivity of the function, which is the thing we talked about a second ago. And that is enough time for differential privacy. That's the big formula. That was going to be my one formula, but we're going to keep going. We can do that from machine learning. Take my word for it. Federated learning. Federated learning. It's very simple. I'm actually going to do this in sort of like one statement. Instead of aggregating all of your data to the cloud and doing your statistical analysis there, that's what we do by default, because that's how our tools are built, you leave the data with the data owners, and you do little bits of statistics at each one of the data owners, and you only aggregate those statistics. Okay? The best example of this, you know, when you're texting and it tries to predict the next word on either Android or iOS, that model, when you plug in your phone at night and you attach to Wi-Fi, a new model comes down from the cloud, it learns on your local texts, updated version of the model goes back up to the cloud and gets averaged with hundreds, thousands of other people's models, right? And the implication is that Google can train a really accurate text classifier without having to aggregate all your tweets into a centralized repository. Cool? That's federated learning. Multi-party computation. This is the most exciting one. This one blew my hair back the first time I came across it. And I'm going to skip the slides for a second and just tell you what it is. So it is the ability to share ownership of a number. Wikipedia defines it slightly differently, but for the sake of this argument, it's the ability to have shared ownership of a number. So I can take the number 5, and I can split it into 2 shares, a 2 and a 3, 2 plus 3 equals 5. And I can give you the 2, right? And I can give you the 3, all right? And now this number is encrypted between the two of you, okay? Because there's no way for you to know what this number is in between you unless you have all the shares. Does that make sense? So you are shareholders in this number. And the interesting bit is that you can actually compute using this number. You can do arithmetic with this number while it is encrypted between these two people. So let's say you wanted to multiply it times 2. If you multiply your 2 times 2, you multiply your 3 times 2, 2 goes to a 4, 3 goes to a 6, and now we have an encrypted version of a 10, right? Because 4 plus 6 equals 10. And there's a whole host of protocols that allow you to do addition, multiplication, comparison, and more complex functions while numbers are in this shared state, while they have this shared governance, okay? Now, the interesting bit is that sort of AI models, data sets, images are numbers. They're big collections of numbers, which means you can take each number and share ownership of that number, and by extension, share ownership of a data set, share ownership of an AI model, share ownership of XYZ statistical computation, right? And everyone who's participating has both secrecy or privacy, right? Because their values are encrypted, And they have shared governance. They get to control whenever anyone is going to use this data point. And now I'm going to make a little bit of leap because we're short on time. If you take the bits of an AI model, right? Let's say one that can classify whether or not you have, whether or not cancer exists in an image, right? And you encrypt all the numbers that are required for that model to make a prediction, okay? And then a doctor does that. They split into 2 shares. Every single number is split into 2 shares. And we'll call it the public and the private one, okay? And then, we'll leave that there for a second. A patient takes their image, right? The image of themselves, right? And splits each of the pixel values into 2 shares, a public and a private. And then they exchange the public version. So if there's a public and private here for each number, all the public ones go over to the doctor, and for the doctor's AI model, public and private, all the public versions go over to the patient. Now, they can do arbitrary computation using the numbers from the image and the numbers from the AI model, which means they can make a prediction while the data and the model are both encrypted. Okay? So they can predict whether or not there's cancer in the image while the image and the AI model are both encrypted, while the intelligence of the doctor and the data set from the patient are both encrypted and protected. The output of which is encrypted and still shared governance between the two. And the final step is to have only the patient decrypt the final result. So the end result of this setup is that a patient's image can be classified, right? Can have a piece of intelligence applied to it, right? Without the patient ever revealing the image to anyone. And without the doctor ever having to reveal their proprietary IP or all the lessons they learned about all the other patients, you know, when they classified their images and got them wrong, like so in the model training process, if you're familiar with machine learning. And the consequence of this is that if with sufficiently advanced infrastructure based on this better trade-off, we can actually have a better privacy trade-off than we do in the analog world, right? Where potentially doctors can give advice, right, based on their intelligence without ever having to hear the inputs from the patient. Because it's the first time that we've ever had the potential for a piece of intelligence, albeit limited, because it's machine learning, not a human intelligence, to prove that it forgets something or prove that it doesn't remember something. Because even though the numbers themselves are encrypted, we know exactly what the computations are happening, right? It's still specific computations over encrypted values. So I hope that makes sense. I hope that you understand the general use case of what we're going for. I hope that you get some intuition about how differential privacy protects your information by adding noise, and how you can have privacy over your inputs by encrypting them using secure MPC. And we're baking all these into standard toolkits to try to make it as easy to use as possible. If you're interested in learning more about this, we recently released a Udacity course. So it's about 6 hours of content that I created in partnership with OpenAI and Apple and DeepMind and some guest speakers from there talking about deploying this in production. And it's free. So udacity.com, secure and private AI course. So if you Google Udacity and secure and private AI, you'll find it.
All right, cool. Thank you. That was awesome. Maybe we have time for like one question. We're a little bit over, so has anyone got a question? Yep.
How does the model adapt to other inputs? So you showed 3 inputs, consultant, the patient, and the output. But normally, so like, if I go to a doctor, it won't be the doctor that does the MRI scan, it will be a nurse. The camera will be another input because it's taking the photo. Because if I don't have an MRI scan, I don't know yet.
Yeah.
Maybe Apple will.
That would be cool.
So, there's other inputs into that model that could be used to attack it. And then also, the underlying hardware is normally how do we deal with metadata. Every time we take a photo, it's always invaded with metadata. And the doctor needs to know the date and time maybe when it was taken. But then using third-party sources like maybe say Trask that you were at the hospital on a certain date and time,
Right. 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 So, yeah, absolutely, yeah. So that's exactly what differential privacy would hopefully mitigate. But so your question, his question was basically, if I can sum up a little bit, how do you do input and privacy in the real world with physical devices? You know, that where a physical device collects the information, such as like an image scanner or something like that. And then there's also like you physically showing up in a hospital somewhere that people can try to reverse engineer what you're doing and how you're doing it. So you're absolutely, this is the right question to ask. And this is something that we're actively working on. So I can give you one technical answer that is a piece of the puzzle, which is even though I gave the example of NPC sharing a number, the 5, between 2 people, you can NPC share to arbitrarily large numbers of people. So in the example on the slides, I think we did 5. So in this case, it's just additive secret sharing. And so if you look at the A, 1 plus -3 plus 5 plus 0 plus 2 equals 5, right? So you can take inputs from arbitrarily large numbers of groups, although it does slow down the computation if you have larger numbers of people. So the protocol doesn't explicitly limit that. Now, however, how do you make it so that you can protect privacy in the real world? The analog world is just inherently leaky. That's a really, really hard question. And unfortunately, if we get to the point where, you know, we're having to worry about people tracking when we're physically walking into buildings, you know, I worry about that myself a little bit with all the availability of sort of satellite imagery and these kinds of things. Isn't there a new startup that's doing the whole world every day? I'm pretty sure there's a new startup doing the whole world every day, like a new image of the whole world every day.
Yeah, and then there's China, which is...
Yeah, and then there's that. For people who want to build infrastructure that goes out of their way to protect privacy and keep track of it, I think that's more of a question of adoption. Like how widespread could we get our infrastructure to respect individuals' privacy and to be built with these kinds of things in mind, not unlike many of the features that you mentioned, where it gets better as more people are sort of adopting it. But obviously, if you just have sort of one institution that adopts it by itself, it can help prevent that institution from divulging private information, but you could still have other institutions that aren't doing that as well. So yeah. Yeah. And trusting hardware is always a scary business.
All right.
All the software
Thank
guy.
you. Thanks, Andrew.
Yeah, thank you.
So, we're going to wrap up. There's some coffees. I think we'll start back at 1:15. So it's the blockchain and 1:45, yeah, sorry. So blockchain and cryptography in here, and then in the downstairs lecture,